In conducting materials such as aluminum, electric charges move readily in response to the forces that electric fields exert. This property of conducting materials has a major effect on the electric field that can exist within and around them. Suppose that a piece of aluminum carries a number of excess electrons somewhere within it. Each electron would experience a force of repulsion because of the electric field of its neighbors. And, since aluminum is a conductor, the excess electrons move readily in response to that force. In fact, as a consequence of the 1/r² dependence on the distance in Coulomb's law, they rush to the surface of the aluminum. Once static equilibrium is established with all of the excess charge on the surface, no further movement of charge occurs. Similarly, excess positive charge also moves to the surface of a conductor. In general, at equilibrium under electrostatic conditions, any excess charge resides on the surface of a conductor. Now consider the interior of the aluminum sphere. The interior is electrically neutral, although there are still free electrons that can move under the influence of an electric field. The absence of a net movement of these free electrons indicates that there is no net electric field present within the conductor. In fact, the excess charges arrange themselves on the conductor surface precisely in the manner needed to make the electric field zero within the material. Thus, at equilibrium under electrostatic conditions, the electric field is zero at any point within a conducting material. This fact has some fascinating implications. Consider an uncharged, solid, cylindrical conducting rod at equilibrium in the central region of a parallel plate capacitor. Induced charges on the surface of the cylinder alter the electric field lines of the capacitor. Since an electric field cannot exist within the conductor under these conditions, the electric field lines do not penetrate the cylinder. Instead, they and or begin on the induced charges. Consequently, a test charge placed inside the conductor would feel no force due to the presence of the charges on the capacitor. In other words, the conductor shields any charge within it from electric fields created outside the conductor. This shielding results from the induced charges on the conductor surface. The electric field lines are altered outside the conductor because the electric field just outside the surface of a conductor is perpendicular to the surface. If the field were not perpendicular, there would be a component of the field parallel to the surface. Since the free electrons on the surface of a conductor can move, they would do so under the force exerted by that parallel component. In reality, however, no electron flow occurs at equilibrium. Therefore, there can be no parallel component, and the electric field is perpendicular to the surface. Since the electric field is zero inside a conductor, nothing is disturbed if a cavity is cut from the interior of the material, as seen here. Thus, the interior of the cavity is also shielded from external electric fields, a fact that has important implications, especially for shielding electronic circuits. Stray electric fields are produced by various electrical appliances, such as hair dryers, blenders, and vacuum cleaners, and these fields can interfere with the operation of sensitive electronic circuits, such as those in communications devices, televisions, and computers. To eliminate such interference, circuits are often enclosed within metal boxes that provide shielding from external fields. The preceding discussion deals with features of the electric field within and around a conductor at equilibrium under electrostatic conditions. These features are related to the fact that conductors contain mobile free electrons and do not apply to insulators, which contain very few free electrons. Now, what happens if we suspend a charge of plus Q inside the cavity of a conductor as seen here? 3 facts will guide our analysis. First, since the suspended charge does not touch the conductor, the net electric charge on the conductor must remain zero, because it is electrically neutral to begin with. Second, electric field lines begin on positive charges and end on negative charges. Third, at equilibrium under electrostatic conditions, there is no electric field, and hence no field lines inside the solid material of the metallic conductor. Now, since the field lines emanating from the suspended positive charge terminate only on negative charges and do not penetrate the metal, there must be an induced negative charge on the interior surface. Furthermore, the lines begin and end on equal amounts of charge, so the magnitude of the total charge induced on the interior surface is the same as the magnitude of the suspended charge. Thus, the charge induced on the interior surface is negative Q. we know that the total net charge on the metallic conductor must remain zero. Therefore, if a charge negative Q is induced on the interior surface, there must also be a charge of positive Q induced on the exterior surface, because excess charge cannot remain inside of the solid material at equilibrium. The electric field lines emanate radially from the conductor, as if only the suspended charge existed there, and the conducting shell did not. It's interesting to note that you could observe the electric field of a charge located inside a void of a conducting material, while on the outside of it. However, you could not detect a charge outside a conducting material if you were inside it. In summary, we've discussed the following properties of conductors. First, at equilibrium under electrostatic conditions, any excess charge resides on the surface of a conductor. Also, at equilibrium under electrostatic conditions, the electric field is zero at any point within a conducting material. A conductor shields any charge within it from electric fields created outside the conductor. Finally, the electric field just outside the surface of a conductor is perpendicular to its surface.